Alright, so today I'm going to explain you on Bohr effect and Haldane effect. This is something which will be going on with hemoglobin molecules, especially with oxygen loading and oxygen unloading process. Just to simply put it in a simple way here, Bohr effect will be going on in peripheral tissues and it helps in unloading of oxygen from hemoglobin molecule. Whereas Haldane effect, it will be going on in the lungs and it helps in the loading of oxygen. This is as simple as that. Okay. So let me just start with, I'll explain you what is Bohr effect, which is going on in the peripheral tissue, and then I'll take you to Haldane effect, which will go on in lungs. Okay. So peripheral tissue. Peripheral tissues are metabolically active. So whichever the tissue which is metabolically active, so TCA cycle, that is Krebs cycle, will be going on, and the byproduct of TCA cycle is carbon dioxide. So there will be release of carbon dioxide. So PCO2, that is partial pressure of carbon dioxide in peripheral tissue, it will be more. So that carbon dioxide, so it will diffuse because it's a gaseous molecule, it will diffuse out of cells into the blood, and in the blood it's going to diffuse into red blood cells. So what I will do now is I am going to take this carbon dioxide and allow it to get into red blood cells here. So it means your red blood cells are in the peripheral tissue. So carbon dioxide is getting into the red blood cell. Carbon dioxide gets in here and it is going to combine with the water. And the combination of this will be catalyzed by carbonic anhydrase enzyme. I'll just write it as Ca, carbonic anhydrase. Now with that you are going to get H2CO3, that is carbonic acid. Now this carbonic acid, it spontaneously dissociates into H plus, this is proton, plus HCO3 minus bicarbonate, proton and bicarbonate. Now this bicarbonate, it is going to go out of red blood cell into plasma. HCO3 minus gets out into plasma, and as the HCO3 minus going out, bicarbonate which is going out, chloride comes in, and this is what is referred as chloride shift. Note that this is the carbon dioxide which is present here. If you consider this as 100%, 90% of this carbon dioxide will be carried from peripheral tissues into the lungs as bicarbonate. Okay. Now what happens to the rest, that 10% of carbon dioxide? For that matter, so this bicarbonate range is usually between 85 to 90% or 80 to 90%. Around 5% of carbon dioxide will be directly dissolved in the plasma, which is a dissolved carbon dioxide, which is around 5%. Some textbooks will say 5 to 10%. And rest 10% here, so I'll change this number to 80 here. 80%, I'll make it as 80%. I'll make this as 5 to 10%. Dissolved carbon dioxide, 5 to 10%. Rest 10% of carbon dioxide, it will go and bind directly to hemoglobin molecule. Gets into the red blood cell and it will bind to hemoglobin, that is HP. Note that this red blood cell which is there in the peripheral tissue, it came from lungs. So while it came from lungs, red blood cell is carrying 4 molecules of oxygen. That's the oxyhemoglobin. See, the hemoglobin is carrying 4 oxygen molecule. Okay. Now we need to release these oxygen molecules present in the peripheral tissue. So how to release oxygen molecules? So the proton that is formed here, see the carbonic acid dissociated into bicarbonate and protons. These protons will go and protonate histidine residue in hemoglobin molecule. When the proton protonates histidine residue, this will lead to increase in salt bridges formation between dimer 1 and dimer 2. So that will lead to stabilization of T state of hemoglobin. Because of this, oxygen molecules will be released from hemoglobin. So oxygen molecules, simply they come out into the peripheral tissue. Oxygen molecules are released. 4 oxygen molecules are released. In fact, under normal conditions, a basal condition, only 2 out of 4 oxygen molecules are released. But just for our theoretical understanding here, we are releasing all the 4 oxygen molecules. Otherwise, under basal condition, we release only 2 oxygen molecules bound to hemoglobin molecule. Now, after binding with proton here, hemoglobin is getting into deoxy state. So we have released oxygen. This is what is called as Bohr effect. So the Bohr effect is going on in the peripheral tissue where the carbon dioxide production is more. Carbon dioxide is getting into the red blood cell, combining with water with the help of carbonic anhydrase, making carbonic acid. Carbonic acid spontaneously dissociates into bicarbonate and proton. Bicarbonate move out into the plasma. That is the 80% of the time, 80 to 85% of the time, that is the fate of carbon dioxide. Rest of the carbon dioxide, like 5 to 10%, directly dissolved in the plasma. And rest 10% of the carbon dioxide is directly binding to hemoglobin, that is forming carbaminohemoglobin. Now, fate of proton here. Proton that is released by spontaneous dissociation of carbonic acid is, it is going to go and bind with hemoglobin. It protonates histidine residue in hemoglobin molecule. Because of this, there will be stabilization of T state, which is not favorable for oxygen. That's why there will be release of oxygen. So oxygen is diffused into the blood. From there, it will be taken up by peripheral tissues. This entire thing, we call it as Bohr effect. Okay. Now let's move on to see what is Haldane effect. Now this red blood cell, which is carrying proton and carbon dioxide. So I'll be just writing another red blood cell here, RBC. Note that red blood cell is biconcave shape, just for our like space thing and all that. So I'm just putting it as a spherical shape here. Otherwise it is biconcave. So it has got hemoglobin attached with proton, that's a deoxyhemoglobin, and also it is attached with carbon dioxide. 10% of the carbon dioxide is attached to hemoglobin. So this kind of red blood cell is returning from peripheral tissues to lungs. So this is changed to this one from in peripheral tissue, and now that is carried to the lungs. Now in the lungs, because we are inspiring, so the alveoli has got oxygen 90 to 100 millimeter of mercury. Okay, so we have red blood cell here in the lungs. It has got hemoglobin. It has got hemoglobin with proton attached and attached with carbon dioxide. Now oxygen is getting in lungs. As the inspiration occurs, so you are getting oxygen. Oxygen is getting. Now, and also note that the plasma, when the blood venous return occurs, it has got bicarbonate. So that bicarbonate is also coming along with the plasma. So we have bicarbonate here, HCO3 minus. Bicarbonate is also coming along with the venous return. Now oxygen is getting in. Now because oxygen, partial pressure of oxygen in the lungs is 90 to 100 millimeter of Hg, that itself is sufficient to load this oxygen with the hemoglobin molecule. So oxygen will be loaded with hemoglobin molecule here. So oxygen is loaded now. Because of this, what happens? Because of the binding of oxygen to hemoglobin, that will remove carbon dioxide and proton, both of them, because there will be breakage of salt bridges. When oxygen binds to hemoglobin, it gets into relaxed condition, so there will be change in the conformation of a molecule, and that will lead to breakage of salt bridges, and there will be release of proton. Proton is separated and carbon dioxide is also separated. Now hemoglobin is bound with oxygen. That's the oxyhemoglobin, relaxed condition. Now let's see what happens to the proton and what happens to the carbon dioxide. Now the proton that is released here, it is going to go and bind with bicarbonate. See this bicarbonate which is coming from the plasma, now it is getting in. HCO3 minus is getting into the red blood cell. This is the red blood cell. So bicarbonate is coming into the red blood cell now in the lungs. As the bicarbonate is coming in, so chloride is going out into the plasma. That chloride shift is also going on here. Only thing is bicarbonate is entering, chloride is moving out. Whereas in the peripheral tissue, bicarbonate went out into the plasma, chloride moved into the red blood cell. Now this bicarbonate in the plasma returned to the lungs and it is getting into the red blood cell and chloride is moving out. So this bicarbonate is going to combine with this proton which is just released from hemoglobin. So it is going to combine with proton H plus and that will become H2CO3, that is carbonic acid. Now this carbonic acid will be dissociated into carbon dioxide plus water. Now the carbon dioxide that is dissociated now, it will be exhaled, so it will go out. Carbon dioxide is released. All this carbon dioxide is going out of red blood cell into the plasma. From there it will be exhaled. Basically it gets into the alveoli and it will be exhaled. Okay, as we inhale oxygen, oxygen is going to bind with hemoglobin, remove proton, remove carbon dioxide which is bound to hemoglobin, 10% of carbon dioxide. Rest 80 to 90% of carbon dioxide which is coming in the plasma in the form of bicarbonate. Bicarbonate gets in, proton will bind to it, becomes carbonic acid and that is dissociated into carbon dioxide and water, and carbon dioxide is diffusing out of alveoli, exhaled out. So as we exhale out carbon dioxide, we are inhaling oxygen. So this entire thing, we refer that as Haldane effect. So this is Haldane effect which is going on in the lungs and which is going on in the peripheral tissue. We refer it as Bohr effect. So simply Bohr effect is release of oxygen from hemoglobin molecule in peripheral tissue. Haldane effect is binding of oxygen to hemoglobin molecule in lungs. This is all about Haldane effect and Bohr effect. Thanks for watching.